This is a collaboration between IBM Research and University of Michigan. And I just want to mention that the lead author, the guy who put in the most work, couldn't make it to the talk, but it's a PhD student from University of Michigan, Xiaoen. So I'm going to talk about fault resilient in cloud. And I think I got a great segue from your talk. So let's talk a little bit about what's a cloud management stack. So it's a reasonably new software layer for managing large clusters of machine and providing infrastructure as a service or other types of platform as a service or software as a service. So we have IBM, Smart Cloud, Amazon EC2, Amazon being the most famous, but there are certain cases where you may want your own cloud, something that is either private or has specific needs. And there's a series of reasons for that: security or hesitation from an industry sector, or maybe total cost of ownership may actually be better in certain cases. So this talk is really trying to study this new layer that we as a community can work on. Specifically, I'm going to target OpenStack. This piece of work is really OpenStack specific. And I will start to talk about the details later, but let me start with an anecdote and that motivated this work. So about a year ago, I had never touched the cloud, and I was given the task with a few colleagues to install OpenStack on a cluster. And they told me it should be very easy. The whole community has tons of documentation. Go ahead and install. So I said, great. Read the documentation, download everything, start installing. Everything's going fine. Okay, try the first thing out, doesn't work. Oh, okay, that's okay. I did something wrong. So go through logs and logs and logs. An hour later, oh, I need to flip this bit. Okay, managed to get that to work. And I iterated through that through several days, hundreds of logs on different machines, trying to get the system up and running. Finally got it up and running. I was able to provision VMs. Okay, let's start doing performance analysis. We have these benchmarks. Let's leave it running. Go to sleep. Come back the next day. Everything is in a bad state. So what happened? I don't know. Let's start looking at the logs. So that really motivated, set the scene for trying to understand this work. So it seems that with any initial infrastructure project, be it an operating system or something like cloud management stack, you first try to put in some functionality so that it becomes useful. But then after it became useful, you actually want it to work well, fault-free. So that tends to be usually the second thing you implement. It is rare when the architecture is built from the very first try with fault tolerance in mind. So it's a little bit funny. We've been saying this as a community. Failures are the norm when you reach large scales. So we kind of know this. But in fact, we still see infrastructure after infrastructure still having a difficult time getting over the hump of going from an initial project without fault tolerance and being able to handle faults at different types of levels. So this initial study was just trying to understand, was our piece of hardware really bad and couldn't work well with OpenStack? Was my configuration awful and that's why OpenStack didn't do well, or are there more fundamental problems? So, well, our findings that actually there are fundamental problems to OpenStack, and I guess it would be great if we had more tools or more processes to try to overcome these and transition these software over to a more resilient system. So I'll give a brief overview of OpenStack, and then talk about a fault injection tool that we developed that's very OpenStack specific, and talk a little bit about the issues we observed. So OpenStack is not unlike other distributed systems. It's composed of multiple components. So it has identity service, image service, compute service. It has a lot more that I haven't drawn here. Most of these components communicate with each other through RESTful interfaces. But they also use within the service RPCs. And for the RPC, they use an AMQP broker. Can be RabbitMQ or QPID. There's a central database that stores information about what's going on in your cluster. Well, the compute nodes themselves. So that's just a high-level overview. And let me try to define a little bit what I mean by fault and fault resilience here. So we say that the system is fault resilient when it can maintain correct functionality under faults. And the way we're going to stress test the system is issue external requests, so user-facing requests, and inject some faults to see if the system behaves as it should. And we just think of very simple faults. So service crashed, some transient non-responsiveness, and network partitioning. So we didn't get as advanced as, let's say, the limping hardware case, because this was enough to show that there were issues. And the specific version of OpenStack was ESEX that we targeted. So let me briefly go over our fault injection tool. So we have OpenStack, and we added or augmented the logging framework in OpenStack to be able to watch a external request going through the system as it executes. And that, so what we do is we issue requests to this system while it's more or less quiescent and generate execution graphs based on this request. So let me try to show you an example of an execution graph. Let me try to have you guys imagine what this would have looked like. So we start off with an external request here. It may check if your image ID is correct. And so there would be several services outlined here, and the request would basically be zigzagging between multiple services. It's not really important, the exact graph, but just to get a notion that there are nodes in this graph representing the different services or components, and there are edges representing communication of either REST calls, RPC, or external execution, like or an SQL query to a database. So that's sort of the general graph that this will generate. And so great, we have a bunch of execution graphs that were generated from fault-free execution. So that's how it should be done. And then we can generate a test plan based on these graphs and different fault types that we want to introduce. So we basically walk the graph and explode it, showing, okay, let's insert a fault at this moment in the graph of this type. So we have a bunch of graphs that we use to put into the fault injection controller. So the fault injection controller will spawn a clean OpenStack installation, and will start executing the external request corresponding to that graph, and will execute transactions on that graph one at a time up until you get to the execution point, introduce the fault that you had scheduled, and continue and see what OpenStack does. And after that, we continue logging what's going on in the system, and we have what we call a faulty execution. And this faulty execution doesn't mean that the execution presented a problem. It's just that we had introduced a fault. Whether that fault manifests into a user-visible bug, that's a different issue. And that's what we do in the next phase. So to determine whether that fault that we introduce in that specific execution graph caused the problem or not, we do two things. We look at the output of the execution. So what did the system return to the user when the user had made a request. That's one thing. The other thing was we analyzed the internal state, because maybe the system returned, okay, everything went great, when in fact all your database is corrupted because of a fault. So this is one of the hard parts of our system, where you have to generate a specification by hand, knowing the internals of how OpenStack works. So there are a lot of checks that we can make, like, okay, if I have VM running, then the network belonging to that VM should be registered somewhere, and so on and so forth. So we can generate a bunch of specifications and make sure that those comply with what we observe at the end of each run. So that's pretty much how the fault injection tool works. And these are some results that we collected from a few months ago. We've been working on it, but at this point in time, we categorized bugs into pretty subjective categories, and I will try to go quickly into each one of the categories to explain a little bit more. So one of the things that actually wasn't detected by our tool, but we decided to include in the paper, is there is no out-of-the-box high availability or automatic failover solution. So OpenStack is riddled with single points of failure. So the database is one case, and the suggestion from the community is, well, I know that's the default deployment of OpenStack, but you should know better, and you should deploy an HA solution. Great. Okay, so let's deploy an HA solution for the database, for the AMQP broker, for the individual services. And that reduces the likelihood of certain faults from occurring. However, it doesn't eliminate them. And we've seen this in practice where we had a mirrored AMQP broker duplicating all messages, and still there was a bug in the AMQP service that we were using, and no messages were being sent, irrespective of the mirroring. So HA is part of it, and I think OpenStack should offer a automatic deployment of this, should have this embedded into it, and it's not right now. But that doesn't solve all of the issues that I'm going to discuss further. The other thing that a lot of distributed systems use are timeout mechanisms. I guess we saw a little bit about, had a discussion about this with the limping hardware, and it proves to be quite effective in several cases. So you determine, okay, this service hasn't replied in a certain time period. Let's consider that it's not working and move on. And OpenStack does use lots of timeout mechanisms, but it's not very complete in the way it does it. So one concrete example is compute service wants to start a new VM. It needs an image to do so. So it contacts the image server through a REST call, and if it can contact it, it assumes that it's alive and doing well. But somehow, for example, in our test case, we can partition the network right at that moment, right before the image service is replying. Well, in that case, OpenStack will not use a timeout mechanism. It just assumes that it can talk to the image servers. And then you'll never get a reply. You'll wait potentially hours for that one request to go through. The other awkward issue we saw was cross-layer coordination. And maybe this has some bearing on the end-to-end system argument that we've heard so many times, but this was not appropriately respected here. So we had two layers of two pieces of software in OpenStack doing communication. One is an OpenStack specific wrapper, and the other is the QPID client library, which is used to do the RPC calls. Well, the QPID client library, which is underneath, will try a call some number of times if it can't talk to the broker. But then it'll set that connection as completely broken and will call up to OpenStack. Well, OpenStack is not aware of this behavior from inside of the QPID library, and it basically says, okay, let me try again. QPAD says, oh, this socket, I know the socket, it's busted. So here you go, OpenStack, there was an error, and they keep ping-ponging like this forever, and you never get your request done. Another case that we saw, somewhat similar to the previous, but it's actually even at a lower layer. We have, again, a QPAD client library issuing selects to determine whether a new message has arrived. And it usually assumes that if select returned, then it can go ahead and read. Unfortunately, in some cases, the socket can be closed, and the select is not returning an actual valid file descriptor, but an error. And it may be that the library that's attached to it will do the wrong thing. And then most importantly, I think there were several cases in OpenStack where we needed a periodic check for cleanups to happen. So we had cases where disks would full up because there were stale images around and just lasted there forever. Another case is the one that's depicted here. So VMs transition from the none state to a build state. It gets all the images. It chooses a host to run on. It starts a VM, and then it should transition over to active, and that's when the user can log in. But if you introduce a crash or a network partition in the right place, the scheduler can crash. And the VM gets put into into this build state and never leaves. Because even if you restart the scheduler by hand, it doesn't check that there were ongoing operations. It doesn't check the current state of these VMs. So what we would like to do is introduce periodic checks to say, okay, if I've been building this VM for a day or 2 days or a month, please move it over to an error state so I can clean it up eventually. It doesn't have to be that timely. Because right now what happens is we get to a point with there's so many errors in the system that the only option is to clean everything and restart. But if we want to make this a reliable piece of software, that's not an option to just kick everybody out and start from scratch. So to conclude, well, we believe that if we're going to use things like OpenStack, CloudStack, Eucalyptus, fault resilience is a must, okay? And it doesn't mean that every operation has to work perfectly because there are hardware issues and software bugs, but should work well enough that you can recover from faults and keep the system operating. And so we did this analysis on OpenStack. We found that fault resilience in OpenStack is lacking by a wide margin, we believe. And but maybe I want to leave this talk in a hopeful message. So our goal is to try to invest more in tooling, and I guess as software engineering in general goes of these systems, we can't expect to throw away all the code and say, okay, the architecture was no good, let's start from scratch. Well, maybe even if we academics would like to say that, the community won't accept it. So can we transition from the current state of things and slowly migrate into a fault-resilient architecture, even though we believe there are some fundamental flaws like single points of failures here. And so I think that's one area where we like to move into for future work. So thank you very much.
So did you actually implement this fault tolerance system?
We implemented the injection tool.
Okay.
We didn't improve the fault tolerance of OpenStack. So all the bugs.
No, I understand that. So my question then is, how much overhead does this tool incurs to the system? Because already having a sort of virtualized architecture, it does include
Right.
overhead to the. Plus, if you add, of course, other things like this one, which is useful, but if it slows down too much my machine, I mean, I would prefer just throwing away OpenStack and get another architecture instead of sort of adding patches to it.
Absolutely. So the logging phase is actually fairly lightweight. So we measured at some point it was less than 1 or 2%, and that's the part that we would want you to run full time, all the time online, is that small overhead. The actual replay, the execution that we do to analyze fault, that slows things down tremendously. We're basically adding a lockstep on every single RPC. However, we don't want that to run online. We want either developers or automated system to run that overnight on our separate cluster. So to answer your question, I think 1 or 2% would be expected with the added logging infrastructure and pulling logs around into a centralized place to be analyzed.
Okay, thank you.
Sure.
Hi, John Wilkes, Google. I really applaud efforts to try and make these things more failure tolerant. Let me tell you an anecdote and then ask a question. So here's the anecdote. Many years ago when I was a young whippersnapper, I went to a set of lectures by a guy called Tom DeMarco who described what happened when Tektronix released their first digital oscilloscope. After it had been in the field for about 5 years without a single software bug reported against it, somebody went back and interviewed the 2 people who built that software. And they said, "How did you do this?" And their answer was actually illustrative of a problem that we have. Their answer was, "We didn't realize bugs were allowed." So the question is, how do we change the culture which causes us to permit shipping systems that will not work, and we know they will not work in the face of failures? So I would argue that the things that you're providing tooling and helping patch up are something we should never have created in the first place. So what we need to do is to go fix the problem at its source rather than try and patch up the things that we manage to ship out to the rest of the world. Do you have any good ideas on how we can push tooling upstream rather than leave it till the last minute?
No, I don't. Sorry. I think that's.
It was worth a try. Right?
No, absolutely. I think it's a fair point, and maybe you could argue that all the software engineering tools we do, garbage collection and all these other fancy things are just getting sloppy programming into the wild. But on the other hand, there's a cost, and I haven't seen an analysis of that. And I'd like to see that because I've had endless discussions with people about writing performant code or writing fault-free code. How much would that cost to produce versus having a bunch of people who only know JavaScript write something in Node.js, which is unimaginable to me, at least when I was an undergrad and loved C and assembly. It seems like the industry benefits from a whole. I'm not sure. So I think that's the trade-off that is difficult to answer.
Yeah, I think just to comment on that one, I think this is a broader question that we see in different spheres here in terms of software bugs and in critical infrastructures as verified systems. We probably don't want to go that far here, but there is a trade-off between, especially for community-built services, and even when built by a commercial entity, the time to market versus getting all the bugs out. It seems to me, given the way we operate the software services or software, it's given as is, no guarantees given. So bugs are an externality for the people developing it, and the time to market is an overriding factor for this stuff.
Right.
So I think the bigger question is, will software ever become a guaranteed product, or it's always going to be as is, and bugs are an externality that one has to deal with?
This is entertaining. I think you're asking for a successful class action lawsuit which successfully extracts a few $1 billion from some software provider because of the bugs, and then we will start paying attention. That might actually be the right way to do it.
Yeah, money.
How long was Gmail beta?
Until it got to the point where we had backups on tape. That was when we took it out of beta.
Thank you.